Hello everyone. Welcome to the 14th live session of Bigyan Charchar Asor. Bigyan Charchar Asor promotes scientific temperament and work among students to spread scientific awareness. We also arrange various programs, some online, some offline throughout the year. So today we are lucky to have Professor Soikat Chakraborty among us, and he will talk about a very interesting subject. So we will all listen him shortly. So Soikat was brought up and schooled in the industrial township of Durgapur till class 10. He went on to St. Xavier's College, Kolkata, to complete his high school and bachelor's in physics. During his master's in IIT Kanpur, he did a summer research project on the SINP tokamak on plasma spectroscopy and fell in love with the subject. Subsequently, he joined an experimental plasma group at West Virginia University for his PhD. After his PhD, he was research scientist at the University of California at San Diego for 10 years, following which he joined Auburn University as a faculty. He loves working with students at all levels, PhD to high schools. He also interested in science outreach, soccer, biking, eating, going on hikes in nature, and of course talking about everything. So I will request Professor Chakraborty to speak about plasmas. We all like plasma physics, and it's a very specialized subject. But plasma physics has application in many part of the physics. So all to you, Saikat.
Yes. Namaskar. Well, thank you so much, Dr. Paul, for the very, very nice and kind introduction. And as Dr. Paul said, that plasma physics is somewhat a specialized topic of physics. And I myself learned about it much, much later in my journey of physics, as I said, like during my master's. And so I want to, go through this discussion, you can say a talk or a discussion mostly, like looking at the breadth of things that can be thought to be a part of plasma physics, like applications of plasma physics. It can goes from the from the universe scale to really little integrated circuit, build how to build a cellular phone, that scale. And before going too further, I am going to say that this is going to be a very pedagogical discussion, which means as if we are teaching, like middle schools or high schools, just to introduce the subject to all of you, just to make people aware of the breadth of the plasma physics. So I will not be going into very detailed, say, equations of physics or the intricacies of the research that is being done. And I would, before even going into the subject itself, I would like to give a very special thanks to everybody, and mostly the admin of Bigyan Charchar Asor, which in my mind, it translates to a gathering to discuss science. So we're going to discuss different aspects of science. Let's start with the discussion of science at the very big picture. If you really think, like if this was a classroom or if this was a conference, and we would be interacting with each other, and I hope you can ask questions and I can reply back to your questions in YouTube, is, why do we study science in general? Like scientists study science. Whoever studies science is a scientist. But why? And, some people ask here, why does scientists look like? There's a lot of misconception or myths in the society that, when we are growing up in a small place, scientists are esoteric people who are exceptionally talented. I can never be one. So what does a scientist look like? Like in my mind, scientists are people who are very skeptical, right? We do not believe everything that is told to us. We look for ourselves. We search the answers. We are, of course, hence we are very curious. So between skepticism and curiosity, we should also be very thoughtful. So if you have skeptical, curious, and a thoughtful mind, hopefully, then you can be a scientist. And I find it hilarious that SCT, the skeptical, curious, thoughtful, is also happens to be Shoykot Chakraborty Thakur, the first letters of my word. So it's just funny. But in general, why do we study science? In my mind, to explain natural phenomena. And this is not new. This is not today. This is since the dawn of history, right? As we have been, living in Earth, right? We always wanted to explain natural phenomena around us. And you have to observe the universe very accurately for that purpose. Now, when I say observe the universe accurately, you have to understand and also quantify what we are observing, right? It's not just enough to say somebody is far from me, but how far is far? That quantification, that putting numbers, quantities to something is so important. And what does these two things allow us? It allows us to predict something. And of course, if you predict something, you come up with a hypothesis, you have to do experiments to verify them. So I think this whole story comes together in the scientific method. And that's why we study science, right? And that's the point of Bigyan Chorcha Rasho, right? We discuss what science is. So in that garb, in order to try and understand the natural phenomena in the universe, there are many ways you can actually, you might say, understand it. And one of them is the length scales, right? You can start from extremely, extremely small particles, right? Like here in an example, it says 10 to the minus 12 in meters, all the way through, atomic level, cellular level, the human, our length scales, right? About a meter and a half, to the Earth scale, solar system, Milky Way, and the whole galaxies. And there are different ways of understanding systems at different scales. And there are also different techniques of doing that. Mathematics comes as a very logical setup on which you can do the quantification that I talked about. Physics and chemistry comes in at different energy scales and length scales. And similarly, you can think of biology as life sciences as another whole part of sciences. Again, when very large objects are taken into account, the study of Earth is the whole of geosciences. The study of astronomy is going up to the skies. And then you can also have social sciences. So among the whole gamut of sciences, what is physics? In that sense, you can think of physics is that foundational branch of science which studies matter, energy, and all the fundamental forces of nature. What keeps nature going? What keeps nature moving? What explains all the dynamics that you see in nature, right? And because physics is a study of matter and how energy mix with each other, I would always ask, like in any gathering, if we look around, just look around us, wherever you are, look around you. What are the common states of matter that we see? Of course, we understand solids and liquids and gases. And then again, because we are skeptical and curious, but also thoughtful, right? As scientists, we think that solids, liquids, gases, but why do we give different names to each other, right? Why is a solid a solid? Why is a solid not a liquid? There must be a reason why they were given different names, right? Different categorization, different categories. And then we understand that, okay, the properties are different. Their characteristics are different. A solid is a solid, and we understand it through its density, through its structure. And liquids can flow. Liquids are different than solids. We understand that. And then there's also difference between liquids and gases, right? And gases are even like loosely packed with respect to liquids. But sometimes you also realize it's not only the characteristics, but also the methods of physics that you use. The equations of solids may or may not be applicable to the equations of how we understand liquids. Sometimes not. Once in a while, you can actually have a commonality between systems, like liquids and gases can be called fluids, and the whole field of fluid dynamics can explain or understand both of them individually, right? And with that in mind, we start thinking that, okay, you have solids and liquids and gases, and then you start thinking, like, how do you go from one state to the another? These are the questions that, that increase discoveries in science. Some of them you already know the answer to. And then there are like questions like, are there anything more than that? We'll look at it. Are there anything more? So for example, if I try to understand on the structural aspect, let's take ice. Ice is a solid. We know that ice is a solid, right? You go into the freezer and you can get ice. It's a solid. No questions asked. And atoms and molecules are tightly held in place. They are packed. But if we increase the temperature a little bit, in the hot summer, you don't have to really do much. Just put it in a bowl outside, because the temperature is so high. It's summertime. the ice will melt into a liquid, right? And then the liquid phase, molecules move around each other. There's still some amount of structure. It's totally not individual atoms just flying away from each other, but they move freely. You have shear in the system. Those are liquids. Increase the temperature even more, and for that you might have to add temperature externally, like you put the water on a stove, right? And then you get into the water vapor, which is the gaseous phase, right? And then where the atoms and molecules are moving essentially unconstrained, right? And then the question is, we realize you can go from one step to the other as a function of energy. Like if you increase the energy, you go to solid, to liquid, to gas, right? And people have studied them for a while. And but if you keep giving more energy to water, what will happen? Let's see what will happen. What happens is you start to get the molecular dissociation into component atoms, right? So the electrons, the bonds between these H and O will start breaking. You can have an OH bond, you can have an O independently, right? And that, if you think of that, is the whole realm of chemistry, chemical engineering, right? But what happens if you go even beyond just bond breaking? If you give more and more energy to the system, you start to get to a domain where electrons can be separated from the atom or molecule itself. And if you separate one negatively charged electron, you remain back a positively charged ion. So if the energies in the system is that high that you can have a negatively charged electron and a positively charged ion floating freely in the system, that is what we would call the plasma phase. And again, as you realize, take anything, say take argon as a gas, because it's an inert gas, it's easy to work with. They have many electrons for every atom. So if you can slowly take off one electron or two or three or more and more electrons, so you can get different levels of ionization in the system. Depending on the energy, you can have an ionization where there's only one ionized argon. So argon 1, or actually it's argon 2 in terms of chemistry language. Argon 1 is neutral argon, argon 2 is singly ionized argon. And you can go all the way to fully ionized plasmas. So this is, just remember this in mind, because this is what will help us understand all the things that we are going to talk about. The other interesting thing is, again, if this was a we could talk to each other, we would say, can you think of naturally occurring examples of plasma? As you look around, we see solids, liquids, and gases. Do we see a lot of plasma? That's a question for this thoughtful mind. One example of plasma is lightning, and of course, you can ask, why should we care? The thing is, lightning strikes big buildings, tall trees, aeroplanes, thousands of times all over the world. And there's no place that can be, so lightning is a very energetic phenomenon, right? For a moment, a huge amount of current flows by, that current heats up the system, it breaks down the insulation of the system, and it can allow, this current to flow. And that temperature, the current also produces heat. That temperature momentarily produces the plasma in the system, which glows, and we see that glow. That is the science of lighting. And honestly, history of science is very interesting and wonderful. So if you go back to the history of science, in that sense, lightning strikes were something, again, this is connecting to Bigyan Chorcha Rashor, where we study science, we discuss scientific things that historically people, had lots of ideas about. Like it was, what do you call, like a god phenomenon, a phenomenon that was the wrath of the gods. Gods were angry, and hence lightning comes, right? And yet people found that the tallest buildings in a small village, usually the churches or the temples, the highest buildings, used to get struck by lightning all the time. So how do you square the two? And so there was a lot of discussion in the Middle Ages about lightning, the importance of lightning, and slowly it was discovered it's a physical phenomenon, like most phenomena in the world. And the history of lightning is very interesting if somebody is interested in that. Now, if you go to the northern sides of more to the North Poles and the South Poles, you start to see aurora. Now, aurora is a phenomena, which is a plasma phenomena. This is, particles of energetic particles, ions and electrons, like particles, plasma from the sun comes to the earth, and it gets funneled to the North Poles and the South Poles through Earth's magnetic field. And so these are again the curiosities and the questions, like why do poles appear only on the north? Why do plasma appear on the north, near the North and South Poles of the Earth? And it's not only the Earth. See, this is Jupiter, and you see any planet which has a magnetic field can actually have aurora on near the poles. So then you can again ask the question, like, then why are plasmas so rarely seen on Earth? Because these are the two natural examples. Beyond that, we don't really find many examples of naturally occurring plasmas on Earth. And the reason being, thankfully, the Earth is too cold. The Earth is too cold for plasmas to occur naturally. Because as we said earlier, that higher temperature leads to the formation of plasma. So if you lower the temperature, you will go back into either of the solid, liquids, and gaseous phases. And the Earth is relatively in that Goldilocks zone where the temperatures are perfect to have naturally occurring solids, liquids, and gases, but not plasmas, right? And that's why biology, the cellular things can so easily happen on Earth. Now, what happens when you go above the Earth's surface? As you go above the Earth's surface, over many, many years, people have sent sounding rockets, balloons, and tried to measure, what is the density of electrons. And we see that at different layers, you can have, people have discovered over the years that you have this whole multiple layers of ions, and you can define ionospheres and multiple, like as you go higher up from the Earth's surface, there are zones where you can actually get plasmas. And it is like as you go further and further, these are the zones where sometimes you can see auroras. You can define multiple layers of ions as for the ionosphere. And then the whole area around the Earth, people have even discovered later on that there are regions which are filled with extremely high energetic electrons, and these are called the Van Allen radiation belts. And they are very active, extremely important to satellite motion and stuff. So you must have heard about the International Space Station. These are some of the domains where the International Space Station flows through, like moves around with. And also these are some of the regions where all of our satellites are there. So these extend, this is not really just around a tiny bit around the Earth, but this actually extends multiple Earth radii, as seen in the picture on the right. And subsequently, this whole area, this whole magnetosphere, people also call it a plasma sphere. There's a sphere of plasma at different layers, at different heights from the Earth, all around the Earth. And this interacts with something, here you can see called the interplanetary magnetic field. All in the universe, there's magnetic fields and plasmas around, and they interact with each other. They have different velocities, they have different strengths, and different phenomena like the magnetosheet, the bow shock, the radiation belts, the whole magnetopause, and the plasma sheets. These are formed around the Earth, and these are heavily studied. Like there's so much of research going on this that I will not do justice to explain everything. But just letting you know, there's a lot of plasma above the Earth, not on the Earth, but above the Earth. Similarly, as you go beyond the Earth, I mean, who has not seen a beautiful sunset from, the Howrah Bridge or the Second Hooghly Bridge, right? This is iconic stuff. If you look at the sun, then what is the sun? See, again, the curious mind of human beings. But as we have done more and more research, we have sent satellites, we have tried to understand that the sun is nothing, apparently, but a big ball of plasma. Of course, the sun is our nearest star, right? And we know that all stars are like sun or bigger than the sun. But the range of phenomena. But what you effectively get, it's the temperature inside it is so hot that traditional solids, liquids, and gases cannot exist, and you end up getting this very rich, highly ionized plasma, right? And remember what we said, like why solid, liquids, and gases are differently named, because characteristics are different and the methods to study them are different. In the same garb, in the same way, plasmas are not just gases, because once you have ions and electrons in the system, charges can freely move, as opposed to in neutral gases. And the physics becomes different to study. Well, difficult, yes. And also the equations of physics that we use, the characteristics that we use. And that's why it might not be right to call the sun, a lot of colloquially people say, it's written in the book sometimes, the sun is a hot ball of gas. I don't think that's absolutely correct. The more accurate statement is the sun is a ball of plasma. Okay. And now, because plasmas are so active, and you see these are all different definitions of different things in the sun. The sun has multiple layers internally, but also externally. When we look at the sun, on the surface, we see the surface of the sun, the photosphere, but there are lots of flows of plasmas around it, and little spots where the temperature is a little smaller, it's called sunspots. Then you can have something called solar flares, and there are prominences and coronas, and we'll go into all the details in the coming few slides. But what I mean is, this is a very, very active system, and it's funny if you think of any in the interface of matter, like say boiling water, right? You have water boiling, means you have liquid which is boiling. Then you have water vapor or something, like we have the gaseous state. At the junction of something which is thermodynamically very active, it has a lot of energy, you get these little bubbles. So you might also think of it, just heuristically, you can think of it that the surface of the sun can also have little bubbles that can burst once in a while, right? And this is an example of such a similar plasma bubble bursting through and coming towards the Earth. And they can be humongously large. So this is just to show the scale of these little plasma bubbles. We call them actually coronal mass ejections, and they can create havoc on different things in the Earth. In 1869, there was a big event called the Carrington event. Carrington was a scientist who recorded this very nicely, and you can look that up online later on. And then this plasma can come all the way to the Earth. Now, in this picture, this is only to show the scale of the size of the Earth with respect to the size scale of the coronal mass ejections. But the Earth at this size, in this scale, is not so close to the sun. The Earth is actually far, 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 far away. And so coronal mass ejections don't hit us all the time, or it's not as deadly as it looks like in this picture. But we will see that why is it important to us and how does it affect us in the next slides. But before that, we had a lot of discussions typically that what is the difference between solar flare and coronal mass ejection. So solar flare is usually the radiation, the bright spots on the sun, the brightening of the suns are called solar flares. Usually it comes with a lot of X-ray radiation and also visible radiation. That's why it is so bright. But the coronal mass ejection is the real physical particles that come out from the sun. The stream of charged particles, could be ions and electrons, that come out physically. So solar flares, the radiation from the solar flare travel at the speed of light. So it takes like 8 minutes to come to the Earth. Coronal mass ejections, typically the material goes through all the empty space between the sun and the Earth. It takes like 2 to 3 days. So we can get a little bit of advance notice, if you might say, in that sense. But then what saves us from this hot plasmas coming out from the sun? It's really the magnetic field of the Earth and the magnetospheric plasma that I was talking to you about in the previous slides. So as these are charged particles, they would follow the magnetic field lines. This is very basic physics. We know that if there is a magnetic field line and there's a charged particle, it will gyrate around the magnetic field line. It cannot just directly cross it. And so it hits the magnetic field lines of the Earth, and then it gets rerouted to the top and the bottom effectively, geomagnetically speaking. So it goes to the north and the south poles, and this is what also causes the aurora that we spoke about before. So there's a very beautiful Earth-Sun connection through plasma physics, and this is called space weather. And it's important because, as I said, the effect might not be felt on the ground. We might not be feeling it all the time, but then all the satellites which are in those different upper layers of the Earth's atmosphere, near the magnetosphere, right, beyond the von Karman line, then those satellites get very badly hit. And hence there are lots and lots of missions from different space agencies, NASA, the European Space Agency, and the ISRO, etc., trying to look at the sun and understand the heliophysics, which is the physics of the plasmas of the sun. Helio is the sun, right? So heliophysics missions looks at the plasma around the sun and the Earth in this neighborhood of the Earth-Sun environment. And this is, as you can already gauge, this is extremely important for lots of different things. But if you go beyond the Earth-Sun, this neighborhood of the Earth and Sun, the whole universe is still filled with plasma. We are slowly learning the plasma in the interstellar medium. That's the medium between the stars, right? That's interstellar medium. Because as the sun moves around through the galaxy, the plasma that comes out of the sun is called the solar wind. It's just a name given to the plasma that comes out of the sun, that streams out from the sun all the time. And then you have these explosive events like coronal mass ejections. They all make actually a little bubble around the whole sun, the whole solar system, right? And you can again get similar things like bow shocks and the the whole bubble, and that zone, it moves around with the solar system. Now, what about beyond the solar system? As I said, all the stars that we see are basically different versions of sun-like or different kinds of stars. The sun is one of the stars, right? So every solar system, everything, every little dot in the sky that we see when we look out at the night sky is nothing but another source of plasma, right? So all the galaxies that are stable. Now, if we go to systems where even stars die, right? Stars die violently sometimes by giving off jets coming out and like supernova explosions. Then stars are born in molecular clouds, right? But they're all in an ionized system. So all the nebulas where stars are born, all the supernovas where the violent death of stars happens, so that new stars can be born, are all now different examples of plasma physics. And sometimes, again, when we look around in our room, we don't realize that. But if you look through the whole gamut of the different scales, and then from lightning to the aurora, to, of course, our sun, and then all the the different stars and planets, the nebulas, the whole universe is literally teeming with examples of plasmas. And again, what are plasmas? Ionized gases in their natural environment. And we have to develop the physics to understand that. And when we do astronomy, astrophysics, all the way to geophysics, and of course also understanding how lightning works, right? We want to prevent building of airplanes as technology to prevent us from any damage to all the circuits and electronics, and also the human beings inside an aeroplane when real lightning strikes it. So there's a lot of studies, there's a lot of research that needs to be done to understand the plasmas, and also, of course, if there are any good or bad or whatever effects of the plasmas. And with this, I would like all of you to think about now all the different examples of plasmas that you can think. Now you've got a little big spectrum of different aspects of plasmas. But then I'll stop here with one question: is that these are all astrophysical phenomena. This is going away from the Earth, right? Most of them, the aurora or everything that I talked about. Why are we interested to study this on the Earth? Is it important? And then we'll come to the next part of this. That thank you, Dr. Pal, for changing the slides. Now, because we now have some scientists. When I say we, I mean the humankind, the very thoughtful humankind, the scientists on Earth. We understand, if once we understood plasmas a little bit, and then we ask the question like, how can we study them on Earth? Can we study them on Earth, right? And if we can, how do we do that? Why would we do that? There are so many questions, right? We have to go up to the government to give us funding to study something. So why? And the reason is very interesting, is that plasmas have literally changed our nightlife. Day life, I'll come to that. But nightlife, so on the left is a picture. It's a picture from a satellite which looks at the Earth, day and night. But this is integrated over several days, over multiple days. You take the data, you put them together, and this just shows all the cities that have been bright at night in the Earth. And you can identify Kolkata, you can identify Delhi and Mumbai, Chennai, even all the big cities. And around Kolkata, you can also see a little line, and that line is like the Bardhaman and Durgapur and Asansol all the way going to Chittaranjan, because it's along that train line that goes in and goes into Bihar and connects us to Delhi, right? So, and this picture is, I think, from Park Street, 25th December, Christmas celebrations, and of course our very favorite Durga Puja, right? The lighting. So all this lighting. I did not know this myself, but I'm amazed to know that the physics of plasmas as a scientific endeavor in the laboratory studies of plasmas came out when you have a vacuum tube, like you have a glass tube, you suck out most of the air from the tube, you get some kind of a vacuum, like low pressure, and then you put electrodes and you put high voltages to those electrodes, and you can actually get a plasma system. And the studies of these plasma systems, the detailed research done by professors in the 1910s, 20s, 30s, 40s, have led to all the fantastic development of lighting, different kinds of lighting technology. And they are all done in the ionized state of whatever gas you are putting in. And so this is wonderful to think of. A very, as I said, there are not a lot of plasma applications naturally occurring in your room, but if you look around, you will find lighting and different kinds of lighting, the tube lights, not the incandescent bulbs. The bulbs are different. it's the thermal radiation from the thermal heat of the coils. But the incandescent, anything when you have a long tube, usually is an example of a plasma. Now, also industrially, sorry if the letters are jumbled up a little bit, you can have different kinds of applications of plasmas, because as you already understand, plasma, if we can make plasmas in a controlled setting, in a controlled way, they have a lot of energy in them, and they can also produce a lot of heat. And they can, because of the ions and electrons, we can use electricity and magnetism to control them in ways where we cannot control just very hot gases. Very hot gases will also have thermal energy, but we cannot control them externally by putting electric fields and magnets around them, right? But because plasmas have charges in them, it's ions and electrons in the plasma, we can actually very cleverly work with the principles of physics and get work done. So you can have things called plasma coaters and plasma cutters. You can have plasma can also, because it's high temperature, it can kill a lot of bacteria or virus, and you can use plasma for surface sterilization. This became a very big thing after the coronavirus episode in 2020. I would like to also spend some time on this thing called plasma etchers. And as you know, the word etch means to etch something away, right? And so we actually build these machines in our lab. These are like two parallel plates, electrodes in a vacuum system. If you give voltage in different ways, usually radio frequency voltage, and control everything in a of course in a lab in a very controlled settings, you can these things called plasma etchers, where you have a plasma background, and if you put something on the bottom of that and put a large negative voltage to it, the ions in the plasma will come and accelerate and hit them. And as it hits them, you can really, in a controlled setting, you can etch away molecule by molecule, layer by layer. And that is how we actually build our cell phones. So it's amazing that as human beings learn the art of plasmas and techniques, we modified and made better and better plasma machines. We could now produce cell phones as powerful as computers, like 20 years back or 40 years back. And this is really, if you're interested in the history of science or history of technology, computers as a concept are there for a while. People know how to use digital technology like zeros and ones to do the mathematics of computation and build computers. And there were computers in the 1940s and 50s and 60s, but they were huge. You would need a whole classroom-sized machines, to get some calculations done with a very low memory and a very slow technology. But then with the discovery of semiconductors in the 60s and 70s, it accelerated the process, because before that it was all vacuum tubes. And the discovery of plasma etchers, those machines that we were talking about in the last slide in the 1980s, and you get better and better generations and versions of plasma etchers, that has reduced the size from big bulky laptops to, well, they were not laptops. Your lap would be painful if you put it on your lap, but they were like big bulky desktops, all the way to laptops, and then our cellular phones. So this, you can see, this is an amazing discovery which would not have happened without understanding the physics of plasmas. And yet we don't really know much about it, because it's plasmas are still a very esoteric subject and not taught in schools. But so I hope every time you use a cell phone, or if you're using a laptop to watch this, you remember that in the backdrop, plasmas are working. And then there are many more industrial applications of plasmas. And this is just one attempt of telling that, like, the plasmas can change the surface characteristics. So a lot of surface modification, anything that needs surface modification can and actually uses plasma technology. Even printing, different kinds of printing, because the ink can, like, if you change the surface momentarily, the ink can get stuck onto the sheet of paper much better. Different forms of, so wetting, dispensing, bonding, printing, different kinds of, and lots of spray technologies like spray coatings. There's anything that relates to do surface modification can actually have plasmas working behind it. And again, these are things that I am also learning as I am going on, because I don't work on this field personally. But if you again go to Google, and you can yourself find many applications of plasmas, which apparently we just don't know as a society, because this is very industrial oriented. Similarly, this is a relatively much newer application of plasmas that until now I've been telling you that plasmas are very hot, right? Plasmas are as hot as the sun. But what we have actually found that, human beings are creative, hopefully, right, and thoughtful, that you can play around with the gas that you are sending in. You can have a very tiny amount of ionization, right? So the heat from the plasma can be controlled in different ways. You can turn the plasma on, say, for a few nanoseconds or microseconds, and keep it off for a while, and then turn it back on again. So you can get pulse plasmas. There are different ways to actually have plasmas, like a system which has all the physical characteristics of ionized gases, and yet the system can be cold to touch or cold for the, maybe room temperature or just above. And this can be done in atmospheric pressures. And as I said, this is a relatively new field. Maybe 20-30 years of research has been done. Some of these applications have now come out industrially and has been commercialized in some countries, but we are still studying this, that you can use cold atmospheric plasmas to do a lot of biological effects. Like, you can clean dental devices. You can even treat your tooth. Exactly how, I don't know, because that's not my field of studies. But if you want more, I can find out more. So sterilization of medical devices. This has been seen also that it can kill bacteria from different, food surfaces. Like I am involved in a work from a biology department where they take our plasma machines and put it on the skin of chicken. So they are trying to, make sure that the food we eat is as best as possible. And though you don't need lots and lots of chemicals on the food. So this is kind of an alternative to chemical treatment. Similarly, similar plasmas can be used for waste treatment. As you see, in radioactive places or different kinds of very complex chemical compounds can be broken down by the energy of the plasmas. We have also seen that if you apply plasma to seeds, it can change the surface of the seeds in such a way that it germinates faster, and it is helping the field of agriculture also. And this is a very new domain. We are still doing lots and lots of research on this. So all the young students, school or college, if you're interested in applications of plasmas, you can look into it. You can shoot me an email, I can give you resources for this. So now you can see that, from the minute semiconductor etching, which manufactures all the IC, the integrated chips in our phones, right? And it has also, so right, this is a picture from like 20 years back. But nowadays you can go to like less than 10 nanometer. And we're trying 2 nanometer chips actually in different places. To cold atmospheric pressure plasmas, which can be used for plasma medicine and plasma sterilization. To lighting and plasma TV. You might have heard about plasma TV, right? So every pixel actually can produce a tiny little bit of plasmas. That's how you can generate the whole screen, plasma screen. And plasmas are used in space humongously. We use something called Hall thrusters. And also like Helicon double layer thrusters is something I was working on in my PhDs for space propulsion. Propulsion is a big thing. Like how do you maneuver and position satellites once they're out of the Earth's atmosphere? Once they're out of the gravitational pull of the Earth, per se, like the atmospheric regions, you don't need very powerful chemical thrusters. They're very heavy, it needs chemicals. So you can actually get by with plasma thrusters. So all the satellites, the hundreds and thousands of satellites have used plasma thrusters. Of course, we do experiments in the lab. And then another part, which could be a whole discussion, a whole talk, hour-long talk, could be thermonuclear fusion, which is trying to make this. What is the science which will allow us to make a star on Earth? Like, can we do thermonuclear fusion, like helium, starting from deuterium and tritium? You get helium, and you also get a lot of energy. So, as opposed to uncontrolled thermonuclear fusion, we want to control thermonuclear fusion. And you can only do that in a plasma state, because then you need temperatures to do this. You need temperatures 10 times that of the sun. And we can do that in the lab nowadays, but it's extremely difficult and hence not yet very stable and not for a long time. And hence it has not yet been commercialized. And I think in plasma physics, thermonuclear fusion is one of the biggest goals. It's one of those long-term, it's one of the holy grails of physics. And it is funny that even people who are not related to plasma physics, but they are aware of the whole world. So, for example, I'll take Stephen Hawking. The last book he wrote, at the very end of the book, he was asked, what is the one thing you would love to see happen? And he said, commercialization of thermonuclear fusion, because that is going to help humanity so much because of almost an unlimited free energy production mechanism. But we can always talk about that. But again, you cannot do that without understanding plasma physics. And that's where we are struggling. We are trying hard. We are trying hard to understand that. Now, in that sense, starting from the beginning of what we were discussing and what we are talking, is that you can see that from very low density plasmas to very high density systems, from very low temperature to very high temperatures, and it's we have quantified in the x-axis is the number density per meter cube. You can go for 10 to the 3 is 1,000 particles, say electrons per meter cube, all the way as you see, like 10 to the 33. And then like on the temperature scale, you can go from, and this is in Kelvin, so like 100 Kelvin is like at the lower end of the y-axis, and all the way to like 10 to the 8, which is like 1/10 of a billion, like 100 million. So you can see that for most of this region, you can get different examples of plasmas. When something is very cold and very dense, then plasma ceases to exist. Then you get into the realm of, as we know, gases and liquids and solids, which is very common all around our Earth. But the realm of plasmas are everything other than what we see on the Earth almost, right? So now, once we understand them, we can also connect it to industry. So in the industry, in space, there's a huge range of different kinds of plasmas that people actually study. People do research on them. And once we understand something, then we can actually also turn science into a technological application. So with this, just I'll say that because we are a laboratory, so we make plasmas in our lab. There are different kinds of laboratory experiments that we work on. We have magnetized dusty plasmas. We also have an atmospheric pressure plasma jet, which has been gifted to or stolen by the biology departments, and we love that. We love that. We love the fact that we make something in the lab, and other professors, other faculty, they can find applications for that also. And we also have unmagnetized dusty plasma experiments, and then we have a machine called Alexis, which can do like scaled experiments to space. And we'll come back to that if we get time. But again, remember, we started by saying, what is physics? Physics can be classified in different ways. One way is the length scales. Another way is the energy scales. That's what we talked about. Also, there's big domains of physics. So the methodology that you use to study things which are like human scaled, human velocities, a car, a bus, that's all classical domain of Newtonian physics, you might say. Right? Actually, all the way going up to the solar system, a lot of solar system can be classically understood. Now, when something goes very, very fast, near the speed of light, you go into the realm of relativity. When things become very, very small, you go into the realm of quantum physics, right? And then, of course, there are some philosophical aspects of physics, which, we get a PhD. PhD means a doctorate of philosophy, right? So there's a lot of thought processes involved, how you think. And also, there's a lot of, of course, what the future is. And then I find it funny that we know a little bit. We don't know most of the nature around us. We don't know so many things, and we're always trying to learn more, That's what makes you a scientist. That's what makes you a researcher, right? But this picture, I like this picture because this also tells you all the different aspects of physics you need to know to be a physicist, right? Laws of motion, you need calculus, you need dynamical systems, you need different kinds of, fluid dynamics, chaos theory you need thermodynamics, you need electromagnetism, you need quantum mechanics. You have to understand how waves work. You understand how light gets dispersed. These are all aspects of physics that you will study in class, in school, in college, in your master's as you go through the system. But also, very funnily, these are the things that you have to think about. Of course, you have to think about hard if you want to do plasma physics research. And there are some aspects of plasma physics. There is also something called relativistic plasma physics. But on a regular day-to-day basis, if you're in the domain of plasma physics, this is what you need to be aware of. This is the concepts of these classical mechanics, fluid mechanics, nonlinear dynamics, thermodynamics, electromagnetism, concepts of waves, some atomic theory, because we do a lot of spectroscopy. And of course, when you do plasmas are hitting the materials, when you do plasma material interaction, then you need to also understand a little bit about the material science. And so this is kind of the domain of all the concepts of physics you need to know to be a plasma physicist, right? And again, as I said, it's sometimes called the fourth state of matter, the solid, liquid, gases, and then plasma. It has been discovered in the fourth, in that sense, but it's the most abundant one. It's everywhere. And again, you might ask this question, like, if a gas contains a few electrons and a few ions, is that plasma? I would say maybe not, because there are some characteristics which separate gases from plasmas. And some of them are that they must have long range interactions. Long range interaction means they must have collective effect. And that's what the word plasma is actually means. The word plasma technically means something that can be molded. And something can be molded when you have a collective system, a collective phenomenon. Now, this is going into a little more details into the physics aspects of it. You must have enough number of electrons and ions in the system to ensure this phenomena called Debye shielding, which is you have to ensure that the number of particles inside a small sphere has to be large enough that you can use the concepts of fluid dynamics and plasma physics together. Now, interesting features are it can sustain different kinds of waves and instabilities. There's so many variations of waves and instabilities in plasmas. We call it a wave zoo, a zoo of waves. And as we already said, it encompasses large range of length scales and time scales, right? From nanometers to light years and nanoseconds to millions of years. It can be fully ionized, like a tokamak where you do thermonuclear fusion. It can be partially ionized, like in our lab plasmas. And with that, I think I would ask Dr. Paul to go into our third set of slides, and hopefully I can end in time. Is that in one of the pictures before, when I showed the machines, the devices in our lab, I said we do magnetized dusty plasma and we do unmagnetized dusty plasma. And then again, the curious person might be like, what is dusty plasma? Why are we talking about? We talked about plasmas, but it's dusty plasma. So dusty plasma is that system, that phenomena that happens in addition to electrons and ions in a regular plasma. You also have neutral atoms because it's partially ionized. So you have the neutral atoms. On top of that, if you have little dust particles, a nanometer to micron sized dust particles, which are solid particles, that's what we call the dust. As you know, everything is dusty, right? This room around me looks clean, but it is not. If you shine a light or a laser through it, you'll find little specks of dust. So dust is everywhere in the universe, and it's also in our plasmas. And remember, the plasmas are electrons and ions, and electrons are so much lighter than ions. If I put quantification, that an argon ion is almost 72,000 times heavier than an electron. If you put the numbers together, that could be a homework. But then the velocities and the energies of particles like ions and electrons depends on the mass. And so in plasmas, we end up getting a very complex system where electrons and ions and neutrons all can behave separately. It's one of the examples of, say, you might call it a nonlinear or non-equilibrium statistical mechanics can be applied in these cases. But because of all those phenomena, what happens is the plasma interacts with the dust particle, which is the solid particle. More electrons can come to it than ions in the same time scale. Ions are slower, they're massive. And hence you can get a lot of collective and kinetic and collective effects both happening in the system when you have lots of dust. On the right, this is an example from our lab where you can have like a wave-like phenomena in the dusty plasma. So the plasma is the pink glow, and then you have dust. We are shining a green laser, and the scattering from those dust particles is what we are seeing as the wave in the dusty plasma. And again, you might say, where does it occur? Why do we study dusty plasma? It occurs everywhere. Everywhere in the universe there is solid particles, there's dust. You have all the way, like when the stars are born in this mixture of molecular gases, molecular clouds, but also as they start clumping together, they form nanometer to micron sized dust particles. And you have ions and electrons everywhere in the interstellar space. This whole thing becomes an example of dusty plasma that we are trying hard to understand. There's a lot of active research going on. Now, the rings of Saturn is one of the best and beautiful examples of dusty plasmas. Also, the tails of comets, I did not know that before, but now that the comets have two kinds of tails. One is the ion tail, which remember the sun is always spewing out plasma, solar wind. So the ion tail follows the solar wind. Dust is heavier, it follows the tail of the comet. So you have a dust tail and an ion tail. You have something called noctilucent clouds. When you are high up enough in the Earth's atmosphere, you get like little particles of frozen wall, like ice, little particles of ice. And they form beautiful patterns of these noctilucent clouds. Now, when we try to go to the moon, the lunar dust is an extremely important challenge for NASA or anybody going to the moon to solve, because dust gets electrostatically charged, it sticks to the clothes, and it's a danger, it's a hazard for the astronauts, like for human space exploration. So all asteroids, lunar surfaces are full with dust, and we have to be very aware of that. We are studying that actively, then of course, as I said, like when you are trying to etch something in the processing plant or at the edge of the tokamaks where the hot dense plasma is hitting the material, some of the material can come in, right? When you are either etching or the plasma is hitting your surface, and you can get debris. So dust and debris inside the etching device, or this tokamak fusion devices, it's a nuisance. We don't want it, but we don't want it also means we have to understand the physics of how to study, how to take it away, how to transport the dust away. And to do that, we have to again understand the physics behind it. And of course, we do fundamental science in our labs. Now, the really why dusty plasmas are so important, is that because the dust particles are very massive, and as I said before, that the more massive something is, the slower its motion is. So we can actually extend the time scale of dynamics. We can look at different kinds of dynamics in a very nice way. If you have dust in the plasma, the dust can also act as a diagnostic, like what is going on in different parts of our plasma. The dust can help us understand that. And as in the picture before, you saw that if we shine a light through the plasma, like a laser, the reflection, the scattering from those particles will allow us to identify them. And then we can use very simple techniques, like you can track them, you can use a phone, like a camera, you can track the particles, use Newtonian mechanics to understand the dynamics and the force balances. And also this has been like, if you have hundreds or thousands of charged particles, but you don't allow them to go away, they're all repelling each other. They have the same charge, negative charge, because electrons are attracted faster. It will form beautiful structures, and you can actually look at like a solid-like structure, a liquid-like structure, and a gaseous-like structure. Later on, if you want, I can send you videos where you can actually see them in real time, moving around, slipping by. And this is called a coupling parameter, which is a ratio between the electrostatic energy and the thermal energy. And you can look at self-organization, or you can look at different kinds of solid state like things like melting, liquid crystals and crystal defects. And by using dusty plasmas as a surrogate, we use dusty plasmas to understand other systems. And as I said, the dust has a very small, like we call it Q over M, is the charge to mass ratio. It's very massive and hence slow, which is a great technique. But at the same time, to look at the magnetization and magnetic effects on a large mass becomes very difficult. So when you want to put a magnet around a dusty plasma system, that magnet has to be very big and very large in magnitude. So we go up to a 4 Tesla magnetic field in our lab. And this is Professor Edward Thomas. He started this lab in Auburn. This was the first time when the magnet was in our lab, not set up yet fully. But so this, again, we go back to those devices in our lab. So magnetized dusty plasmas, unmagnetized dusty plasmas. And Alexis is a device where actually, physics is fun in the sense you can make plasmas in the lab. There are different technological aspects, techniques to do that in the lab, right? But you can also study physics in different ways. It might not be the same density as space or same temperature as space, but you can write equations and connect them. You can non-dimensionalize terms, and you can scale laboratory experiments to space plasma. So while in the Alexis device, which is on the left, we do laboratory plasmas, but we learn a lot of things about the magnetosphere of the Earth just by doing. Also, the fun part is we cannot change the magnetosphere. We cannot change astrophysical systems or astrophysical phenomena. But in the lab, we can actually change the magnetic field, change the pressure in the system, change the power of the system. So we can do a lot of very controlled scaled experiments. And this, like to the field of understanding astrophysics and space physics, this is also one domain where lots of different groups over the world study on. And of course, we do dusty plasmas. And all our devices are made in such a way, the machines are designed very accurately in such a way that you can take one of these machines and put it inside that big magnet that I showed you before. And every graduate student in our group has their own plasma, their own topics, and it's fun to work with everybody. And also there is, as I said, dust is massive, so the Earth's gravity affects the dust. What do you want? What can you do if you want to study the dust and the plasma interactions, which is happening in space, but without the gravity of the Earth? The best thing we can do is go to the International Space Station. So there are professors in Auburn University who actually does, and there's professors many places in the world who does International Space Station experiments. There is actually a module called the Columbus module where you have a dusty plasma system, and we can connect to them with all our computers, and there's a lot of safety regulations, but we can actually work with the cosmonauts and the astronauts in that area to do our experiments as elaborate systems, and it's beautiful when we do that. It's fun. So before ending, I would also like to acknowledge all the group members, right? So Professor Edward Thomas, he started this lab. Professor Uwe Konopka does the International Space Station experiments. We call it microgravity experiments. Professor Eva Konstantinova is the theorist, so once in a while we would discuss different aspects of plasmas. I joined Auburn University in 2020. This is my 6th year. In the last few years, we have like 5 PhDs coming out, like Misha, Lori, Steve, Bhavesh, and Jared. And we have a couple of postdocs and a lab manager, like Chris Cameron is our lab manager, Eli and Jalan are postdocs. And currently we have like 7 PhD students working in our lab. It's fun to work with them. It's a lot of work, but it's fun. Like Elon, Siddharth, Blake, Michael, Jacob, Ash, and Cordell. And, we work in the lab hardcore, but we also have fun. We have fun discussions, discussing physics. We have fun during Christmas. And it's good to understand that, this all hardcore fundamental research, it's a lot of science in it, but the human beings behind who are doing this is equally important. And also just because I'm crazy, so I also love working with high school students and undergraduate students. This is like in summer they come over, we work with them, and they break open things, we put them back together, and we have fun in that way. We also do a lot of public science advocacy and public engagement and outreach. We go to different science fairs, and I think it is nice. I wish more and more administrators would allow scientists and professors to go out and do that. You can go to a local high school and talk about science and talk about plasmas. You can go to a science fair. You can go to Birla Planetarium and do something, And also, it's equally important, and I learned it more recently, much later on in my life, that science funding is an important thing, right? So sometimes you have to go back to the government and talk to the congressmen, the congresswomen, and their secretaries. There's a Department of Science that you have to interact with and tell them about what you are doing. Why is it important? So there has been times where I was in Washington, D.C., there's the Capitol Hill, and with my colleagues, just having fun, but also taking important steps to make sure that you have more scientific literacy in the community. And you will be amazed to know that India, US, any country, there's a whole distribution of people. There are people who believe in science, there are people who do not believe in science. There's always an effort. And so, again, I would thank all of you for patiently listening to this. And also, this goes back to the Vigyan Charcha Ashor, where this is what we need. We need science literacy in our society. With that, thank you. And please, you can feel free to email me, go to our website. You can know more about plasmas. And if you ask questions in the YouTube channel, I can answer them later on. So thank you.
Thank you very much, Saikat, for such a nice talk. So now we know that the plasma is everywhere, basically. It's not only in the celestial outside of the Earth, like in the sun is made of plasma, and in the astronomical context also you showed that in the interstellar medium and everywhere basically it's there.
Right.
And plasma is now we can see the use of plasma in our daily life also, as you mentioned that our computer, the monitor, our part of our mobile is often made of plasmas. So I am having a few questions. So actually, people are showing very much interest in your talk, but questions, all of them are not from plasma physics. So first one is from Anandada. It's I'm just showing the question in the screen.
Thank you, Anandada. Well, I have to also say that Anandada was one of my professors when I was a bachelor's student in St. Xavier's College, and he was one of those people whom I always wanted to be like him, and because it's just exceptional. So thank you, Anandada, for patiently listening to this. And this question is, in my professional opinion, which is more likely to lead to a practical breakthrough in fusion, tokamaks or laser fusion? The word practical makes me think that it would be tokamaks, which is magnetized confinement of plasmas for a fusion device. Now, laser fusion has shown some good results in the last few years of getting the yield, the energy yield, but it's so complicated as of now, until some new technology is developed by by researchers. Um, it's very hard to change the sample. So the amount of energy comes out in one shot is large, but you cannot do multiple shots. So it's also the commercialization aspects is possibly. We are hoping, we are expecting based on the physics to come from tokamaks, which is magnetically confined toroidal fusion devices.
Yeah. So other maybe a novice questions. We know that in our Earth, we don't see plasma physically. I mean, means in nature, we have very few example of plasma like thunderstorm you mentioned. So is it a boon for us? So can you please link the existence
Yes.
of life
Yes.
with the lack of plasma
Yes,
in our
yes,
Earth?
yes. Right. Absolutely correct. And if this was an interactive, like in the classroom kind of a thing, actually, usually I stop on that slide where it says, "Why don't we see much plasmas?" And I use the word "thankfully," and that thankfully, the audience is also connected to that. That because Earth is too cold for the plasmas, hence it has allowed sufficient amount of time for molecular reactions to come together. If you think of organic chemistry can happen, cells
Yeah.
can grow, the whole biological aspects would not have been possible if
So complex
Earth was in a higher
molecules
energy.
was produced
Right.
due to the fact that the temperature is not so high and there's
Right.
not.
We are lucky. I would say,
Yeah.
people talk about the Goldilocks zone.
Yeah, there is no doubt that we are very very lucky.
Very
Yeah,
lucky.
but in this context also,
In this
so that
context also, and
yeah,
because it's a science discussion, and of course also I like to talk too much, as I said,
yeah,
that
yeah, yeah. Yeah,
not
welcome.
only we are lucky in terms of the temperature, the earth is cold enough, we are also lucky that we have a strong relatively, among the different planets, a relatively strong magnetic field around the earth that saves us again and again from the plasma that comes out from the sun. So we are lucky in multiple aspects.
Okay, so I have a few more questions. I'm just putting one question here. It's from
Sure.
Indrani Chatterjee. She's asking that she's from class 10 and she want to work with plasma at home.
Yes,
So
the answer is, I think I really like this question because it's not only a question, but also she's thinking about the safety issues. I really like it because that's what
yeah,
we
yeah,
do.
yeah, 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 yeah,
You
yeah,
can
yeah.
work with plasmas at home. You can. Your parents might be angry at me for saying that, but also the safety aspect is very important because as you already understand that to get plasma you need very high voltages. So even people have studied different kinds of arcs, the formation of arc, the arc phenomena. It's an example of plasma in a sense. Now, if you want to do controlled plasma like in a laboratory settings, you would need more things like you would need a vacuum chamber and things like that. And um,
So this is also
that is also I am
question
seeing
from
and I'm
related questions. So yeah,
making me think, suggest some projects that you can make at home. Again, I
yeah,
might take some more time to give an answer back to you, say on YouTube or something. There are
yeah,
many projects you can do, but I don't
yeah.
know what is the
But well,
safety aspects. Right? Is it safe enough for you to do? Because it also needs a lot of high voltages, high current sometimes, and you should not do an experiment where you try to do that experiment, something happens because as we know, no experiments in the world goes correct the first time. You might actually you can have a power grid failure. You don't want that. You don't want to you don't want to damage anything in the system. But I know people here also that they have in a small garage or in a small lab at one corner of their basement of the house or something. They work with electrical. So you can honestly you can start with learning electronics a little bit, how to use electronics and electrical appliances, electrical things. And as I said, like a tube light that we have is typically an example of a plasma. So if you understand how a tube light works, or if you want to work with it, understand its physical properties or understand something, you can actually do multiple little things at home too. And then I would, another thing I missed saying in the talk, but this is a good time. Thank you for the question. There are lots of universities in India now that works in plasma physics. A lot of professors in different places, different universities are not necessarily only the big national labs like Shah Institute. There's an institute called the Institute of Plasma Research in Gandhinagar. They do very good work. Lots of PhDs come up from there. But there are many other places, not just the IITs. There's now some of the IITs have plasma physics professors there. But there are many universities also that you can actually go, and there's a professor connected to plasma physics. I know Jadavpur University has a few professors, and you can do a lot of theoretical work, related to plasma physics from any university. And so, if you're interested, I would say use Google, reach out to your professors, reach out to your school teachers. They might know more. They can connect you to plasma-related phenomena, so you can make that a future career for yourself.
Yeah. So, here is another very basic question from Sopon Modok. He's asking how plasma forms.
I love this question because this is something that as a species of human beings, we did not know for so many centuries. And now we know. Is that if you think, let me turn the question around with another question, right? Like if you think, how do you get water from ice? The final answer would be you have to increase the energy of the system. Ice has to melt into water, right? Similarly, the lower energy state where you don't have plasmas is the gases. So you can start with a gas. If you put more and more energy into the system through different ways, it could be an electric arc, it could be radio frequency waves, it could be microwaves. You can actually ionize enough number of particles in the gas. By ionize, I mean separating an ion and an electron. So you take an electron away, what remains is an ion. If that separated electron and ion state becomes the normal state at very high energies, that is what we call plasma. So basically you start from a gas, put more energy, you can get plasma. There is one exception to that rule, is also that if you have a very, very, very powerful source of energy like a laser, and that is what Professor Ananda Das also mentioned, the laser fusion. If laser can hit a material, but if you reduce the spot size of the laser to very tiny to increase the concentration of energy, then you can get plasma right away from a solid state. So say if you have a carbon target and you hit it with a laser, very, very powerful, so the most powerful laser in the world, and you can actually get carbon plasma right out from there. That is one exception where you don't need a gas to start with, but otherwise, usually, if you start with a gas, increase the energy, you can get plasma. That's the recipe of getting plasma.
Yeah, probably the last question, but this is not related with plasma physics. He or she is asking basically we need higher dimension.
Dimensions in progress.
Yeah.
Well, it's a very interesting question, and you might say plasma physics. The classical description and domains of plasma physics don't need answers to that, but it is also again a
but it's a basic physics question. Yeah,
basic physics, but also like what do we understand by dimensions? When you say dimensions, a lot of us, me included, initially always thought dimensions mean one dimension is a line, 2 dimension is a flat piece of paper, and 3 dimension means a volume, like a dice or a ball, right? But in physics, when we do the studies and mathematics of physics, dimension has a bigger meaning. Dimension actually means how many independent variables you need to describe a system. So for example, something that is geometrically one dimension, say a little ball moving along a straight line, a bead on a straight line, I can do mathematics in such a way that it could be, in my mind, 2-dimensional system where I need the position of the particle and I also need the velocity of the particle to describe the system. Say, imagine if to describe the system, I need both. I need 2 variables, position and velocity. In my mind, it becomes a 2-dimensional system. Even though geometrically it is 1-dimensional. So when we think of dimension in that mathematical aspect, we already start to see that, say, if you have 5 particles, and for all 5 particles, imagine that we need position and velocity, it becomes a 10-dimensional system. So dimension, take the word dimensions with a grain of salt when you hear different discussions of physics, because it can mean different things more than just geometrical dimension that we usually understand. And that will actually help you understand and think about why we need more dimensions to explain some things in more details. with that, I would probably stop, because it's a that could be a talk in itself about dimensions, right?
Yeah. So thank you very much, Soikot. Today we learned a lot about plasma physics, and I hope that the students will get benefit from that, and especially students like us, old students also actually at least enjoyed it a lot. So yeah, so with this, let us finish today's session with thank to you.
Thank you.